So we've been looking at these arbitrary index collections of subsets, right? So things like U alpha, alpha in A. So this actually gets close enough to foundations, especially when later on when we are dealing with products, we are not going to be talking of subsets of a fixed set, but arbitrary collections, index collections of sets. Okay, so we'll look at this in a little more detail now, or more precisely now. So first of all, suppose S is a set. Then 2 to the S, or power set of P of S as it's denoted, is called a power set of S. So maybe that minus is confusing. So power set of S is a set such that some A belongs to 2 to the S if and only if A is a subset of S. So now you might ask, how do we know there is such a set? Does this exists? By an axiom. There is a specific axiom which either, depending on how you formulate things, either tells you there is a power set or tells you there is a bigger set from which you can restrict to construct the power set. But essentially power set exists by an axiom, and in mathematics people usually make general noises about how something is not a set, it's a class. So that's exactly the power set distinction. Given a set, we can talk about the power set of a set. It exists. I mean, not only we can talk about it, but it exists as a mathematical object. But given a class, the power class of a class leads to paradoxes if we allow it for arbitrary classes. Okay. So now what is an arbitrary collection? You can think of X alpha. Well, X, I have said it's a set, but it could be anything, topological space. First let's take subsets. So a collection, so we used U for open sets and X usually for the spaces, so let's use a more neutral term. S alpha of subsets of X. So let me say fix X. Here it's just a set. So then a collection of subsets of X is, well, what's it? A set A, which is the indexing set. In the case of sequences, this would be natural numbers. Okay. And a function from A to the power set of X, okay, which will associate to the set A. Not as a set A, but an element in alpha A. Alpha in A has associated to it the set S alpha. So this is what we would mean by a collection of subsets of a given set. Okay. So given these, we can define unions and intersections, and that's what we need. Union, okay, is now they're all, union is going to be contained in X. So that makes foundations easy here. X in X such that we have an obvious property. There exists alpha in A such that X belongs to the set S alpha. So this is what is called the union alpha in A of S alpha is by definition this. Okay. Now one of the axioms of set theory, the axiom of specification, says that if you have a set, you can cut it down by using a formula. What a formula is something, an expression like this. So to formalize that needs first order logic, which we will not touch here. But the key point is that when I have a set, I can define a subset of it, and the subset, the union, is those elements that are in some S alpha, which means this way, and similarly the intersection is those elements that are in all S alphas. Okay, so intersection is, which will be denoted alpha in A of S alpha. This is the set of all X in X, and this time for all alpha in A, X is in S alpha. Okay, we'll look at some examples and basic properties first, and then we will look at now unrestricted collections. The basic properties in restricted case will give a hint of the issues that come up. Really, one issue that comes up in the case of unrestricted collections. So let's look at something which is a degenerate case, but it's important and also illustrative. So empty unions and intersections. Okay, so in this case A is the empty set. So we have an empty collection. So then union alpha in empty set of S alpha is the set of all elements. Again, of course, we have fixed x's. So here again S alpha is contained in X. So it's the set of all elements in X such that there exists alpha in the empty set with X in S alpha, and there is no alpha in the empty set. So there's no chance of this property being true. So this is the empty set. This is no surprise at all. An empty collections union is empty, just like with an empty sum. But how about an intersection? If I look at alpha in A, S alpha, this is going to be X in X such that for all alpha in the empty set, some property is true, X in S alpha. Okay. Now I should emphasize, for all alpha in empty set something happening is always true. This is true vacuously, okay, because there is no alpha in the empty set. So every property is true for these. Okay, this is the vacuous implication. It's a slightly confusing at first part of logic, but that's the only way to make things consistent. And you can make any proper set of formal rules will give you this. So this is all of X. So an empty intersection is the biggest set you can get. Okay, so this is one important point to note. So empty union is empty set, empty intersection is these. Now we can write down various other properties like unions of unions. These will involve making disjoint indices. I won't do that. We'll assume people know this kind of thing. As it go along, we'll clarify. But anyway, we need to note down one more thing which is important. De Morgan's laws, that we can interchange intersection and union. Since we'll do that all the time, it's worth stating these precisely. So X minus, if I take the complement, this is the set complement of union of alpha in A. So again, for an arbitrary collection, this is going to be the complement intersection of complements equals intersection alpha in A of S alpha. Not S alpha, of course, but its complement. Now, when you first see this in school, you probably see it as complements. But set complement is slightly disturbing, because what do you mean by not in the set? Means is everything in it? It's better to be specific and say complement with respect to a specific set. And everything is assumed to be a subset of that specific set. So what is it here? So I'll write down a proof as we'll have the where we have to check that an element is here if and only if it's here. Okay, and both of these sides contain only elements in S in X. So let me say little x belongs to X minus union of alpha. When I wanted to say this, let me be a little bit clearer. As for X in X. Okay, and if X is not in X, it doesn't belong to either side. X belongs to X minus the union of alpha in S of S alpha is equivalent to X does not belong to union alpha in S of S alpha, and this in turn is equivalent to saying that there does not, so not, this symbol here is not, there exists alpha in S, X belongs to not S, A, the index set. Oh, My index set has mysteriously become S in many places. It's not, of course. It's alpha in A, alpha in A, alpha in A, X belongs to S alpha. So this is the not symbol. But the basic bit of logic which you must know is that if we say not there exists, it is for all the not. So this is for all alpha in A. It's not true that X belongs to S alpha. Which in turn, by definition, is telling you that this is equivalent to for all alpha in A, X belongs to X minus S alpha, that is equivalent to X belongs to the intersection of alpha in A of X minus S alpha, which is what we required. Yeah, so this is the right hand side. So now we have a similar thing where we flip the unions the other way. We write X minus intersection alpha in A of S alpha is going to be the union of alpha in A of X minus S alpha. The proof is almost the same, except that there exists and for all are interchanged throughout, and the flipping of not works the other way as well. How about completely arbitrary collections? Okay, so we want X alpha, alpha in A. Okay, so collection, indexed collection of sets, maybe spaces, etc. Because sets look a little special here. We'll have to consider this when we look at products of spaces. So we used the fact that they were all subsets of a given set previously. We can't here. So what we do is we axiomatize by the graph, by gamma, which formally is just this. But for psychological reasons, I'm going to write gamma to remind you that it's a graph, and remind myself that it's a graph. So functions are identified by their graphs generally when we axiomatize things, at least in the standard ZFC foundations of mathematics. So gamma is this. So what do we know? First of all, every element in this graph is a pair. So if you have an elemented graph, then there exists an alpha in A and S in a set such that X is so S is going to be S alpha here in this X alpha in this case, such that Xi is going to be equal to the pair alpha S. If you are interested in foundations formally, Kuratowski's way of describing it is it's a doubleton set which is alpha and alpha S. This guy has exactly one element, this guy has two elements, and you can see that this determines the pair. So pairs are equal if and only if as sets, if and only if these things on the right are equal as sets. Okay, this is just out of curiosity. So you want to axiomatize by these. So that means an index collection, an indexed collection gamma is let me be specific and say indexed by A is, so if we have fixed our index at A, we would have this kind of a few more properties, this and some more properties, otherwise sum A together with these properties. So any element is a pair, it sits in the graph, but also of course we want it to be defined at every point. So for all alpha in A, there exists S, a set. I'm saying a set because in set theory everything is a set, but we would want to replace this by spaces, for example, or groups or whatever else you want, such that alpha and S is in gamma. Okay, so here S is going to be X alpha, or rather I should say X alpha is going to be defined to be S with this property. But of course you want this to be well defined. So for that you need for all alpha in A, and for all S1, S2 sets or groups or spaces or whatever, alpha, if alpha S1 is in gamma and if alpha S2 is in gamma, so these are both values of the function, then they have to be equal to each other. S1 equals S2. Or equivalently, the pairs alpha S1 equals the pair alpha S2. So these are arbitrary collections that you want. Okay, so now given these collections, what can we do with them? We can take unions. Union. So union alpha in A, X alpha, is a set with the property. So now we have to say sets. If there are spaces, we take underlying sets or something like that. So X is a set with the property that X belongs to union alpha A, and X alpha is equivalent to there exists alpha in A such that X belongs to X alpha. Now this formula makes complete sense. It's a set with a certain property. An element is here if and only if there exists alpha in A such that X belongs to X alpha. Now one of the axioms tells you a set is determined by its members. So there can't be two sets with the same property. However, is there a set at all? So exists question mark. Well, answer is by axiom of union, etc. Okay, so I won't go into deep into foundations, but in fact you have a specific axiom which tells you that given sets there's a set which contains the union, strictly speaking. Well, but that is not for index collections, that's for actual collections. And then there is an axiom schema of replacement which will let you actually go from the index collection, the graph, to its image. And so that will let you construct in 2 steps the set. Okay, but the important point to note is that there is specifically an axiom which tells you such unions exist. We cannot simply define it as a set. Okay, just a reminder to people, the reason I'm making such a fuss is that if I look at X is the set of all X, or maybe X is psychologically bad. So suppose I look at the set X such that I look at the set of all S such that S does not belong to S, and then you ask the question, does X belong to X? You see, if X does not belong to S, by definition it belongs to S, and so X does not belong to X implies X belongs to X, and if X is in X, then it violates this property, so it does not belong to itself. So this is the paradox of Russell, or Cantor had more or less this in greater generality even earlier. So this is why we're making a bit of a fuss. You can't just write down a set of elements that satisfy a property or you get paradoxes. Instead you have to construct sets. And most of the axioms of set theory are actually ways of constructing sets. Okay, so you couldn't just write down the set of all X such that there exists alpha such that X belongs to X alpha. I mean, you could write it down, but there need not exist a set with these properties. And if you permit such sets, you get paradoxes. Okay, and how about intersections? Okay, so intersection is alpha in A, X alpha is a set with property X in intersection alpha A, X alpha, if and only if for all alpha in A, X belongs to X alpha. So again, we wrote this down, exists. Answer is no if A is empty. Okay, because we have an empty intersection means that it's a set such that for all alpha in A, X belongs to X alpha. But if this is empty, so if we are in the special case where this is empty, for all alpha in A is automatically true. So it means every element, and every element of what? Every set has to belong to X intersection of X alpha. So in particular, the set of all sets you can construct using this, and as I pointed out, it leads to paradoxes. So we cannot talk about arbitrary intersections unless we know if it's not empty. Okay, so if A is not empty, say alpha 0 is in a one particular then so then you construct and it's quite easy to see that this satisfies the property. So sorry, that thing is so horribly written, I'll rewrite it. So if A is here, so say alpha 0 belongs to A. Well, the point is that intersections become smaller. So we know that it has to be contained in X alpha naught. And once we have a set, we can construct smaller sets by using the axiom of specification. There is no danger of contradictions from that. So we look at all X in X alpha 0, not these kinds of unconditional elements, such that for all alpha in A, X belongs to X alpha. So you do this construction, and now it's an easy exercise to show that this is in fact an illuminating exercise, not hard, not that easy, to show that in fact this is actually intersection, that is, it has these properties. You have to see a couple of cases. So if X is in the X belongs to this set, you want to show if and only if it's in the right hand side. So if it belongs to this set, well, it satisfies these properties, so it satisfies the property on the right hand side. But conversely, if it satisfies the property on the right hand side, by specializing to alpha 0, you note that X belongs to X alpha 0, and then it also satisfies this property. So because of the right hand side. So we really do get an intersection. So we can talk about intersections of non-empty collections. I mean, we have a well-defined set corresponding to them. We also have sets corresponding to unions, including arbitrary union. By the way, again, I should emphasize here, if A is empty, union alpha in A of X alpha, no matter what this is, well, this is of course the empty collection, is empty. So an empty union is empty, an empty intersection is not defined at all. There is no such set with this property. Unless you make it a conditional intersection, they are all subsets of a given set. And if you have a non-empty intersection, you can construct a set. So you can always define what it means to be the intersection. It just does not exist if it's an empty intersection.